Section 10.3, as I mentioned in 10.2, is really just a continuation of 10.2. We looked at a bunch of different types of data displays. Most of them were graphs, some of them were tables, and we're going to continue looking at a few more in Section 10.3. The first one that we're going to look at is called a line graph. Line graphs are really, really common. These are line segments that connect one data point to the next, typically showing the trend of a variable over time. Think connect the dots. So it's showing something that's changing over time. For example, if you were to go out and look on the Oklahoma website that's taking care of all of our COVID data and collecting all the COVID data, they have a line graph out there over time. It looked far more like line graph, like connecting pieces like it's describing here with these line segments early on. Once they've connected so much data, the lines, because it mushes it all together, start to look more like curves, but it actually still is a line graph of data. So it's actually very interesting the way that that works over time. Smaller sets of data look far more like a line graph that this is describing. So what you're going to do is you're going to be looking at data sets where you connect the dots in order. So we're going to look at a set of data that talks about studying times for a student over a given week. So learning specialists tracked the average reported study times of her students, and we're going to create a line graph for the data she tracked. So you can see the reported amount of time spent studying Monday, Tuesday, Wednesday, and so on in this given week. So what we're going to do is we're going to make our X and Y axis, or our horizontal and our vertical axis if you prefer. And much like we did last time, we're going to mark along the horizontal and vertical axis what our data is representing. So the time is always going to go on the bottom, right? The change in time. So in this one, it's actually days of the week. So we can label them Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. And mine's not quite long enough. Let me make it a little longer. And we have Sunday. They should be roughly evenly distributed. It's not like I'm looking for perfection here, but they shouldn't look like one's twice as big as the other one, that kind of stuff. We need to label this. This is the day of the week. And then along our vertical axis, we have the hours that we're going to spend studying. So I'll just label that first. So you can see in your chart above that the smallest value that you have is 0.25 and the largest is 2. Does that look right? So everything also, as you notice, is in 0.25 increments, right? Everything's measured to the nearest quarter hour. So as we're making our hours studying, axis over here, it's a good idea for us to measure them and mark them out in quarters. So each of these are going to be a quarter. I don't know how many I have so far. I'll go back and try to make sure I've got enough. Let's see. So the first one would be 0.25. I'm going to label every other one just so that it's not too busy. Here's the number 1. Here's 1.5. We need to make it a little bit taller. And then up here's 2. Is everybody good so far? Okay. We're going to plot a dot for each one of those. So lining up Monday with the 1.5 hours and so forth. So I'm going to do my best to get a reasonable display from my view, and you do the same. So here's 1.5 for Monday. Tuesday is 1.75. It's not good. Maybe that's a little bit better. Wednesday is 0.75. Thursday is 2, probably because they all have tests on Friday, right? And then Friday is 0.25, and so is Saturday. I think they're lying. I think it should be 0. That's what I think. And then we have Sunday, and apparently they got to get back in the groove for going back to school because, school's starting on Monday, and so on Sunday we have an hour and a half. Okay, it's pretty close. lines are much better. If you have graph paper, feel free to use it, but you don't need to go get any. And we're going to connect the dots. So in order, we're going to go from Monday to Tuesday, Tuesday to Wednesday, Wednesday to Thursday, Thursday to Friday, Friday to Saturday, and Saturday to Sunday. So it looks like that. So this shows how it's changing over time. Some graphs look at longer time spans. So one of the places that you will see line graphs used a lot is when you're looking at like the stock exchange. So if you ever have investments and things like that, you can look at the growth or the decline or the growth and decline over time. How things happen in cycles sometimes too is helpful information, right? So if the sales go down every summer and they go up every winter, then you don't have to be worried when they go down every summer because it's expected, right? So you're looking at how something's changing over time. So this is a line graph. It does need one more piece of information, a title, you're right. And so we're going to write that to the side or above or below, wherever you have space is fine. This is the time spent studying by students, or some derivative of that, right? Some variation of that description. Any questions on that one? This one's super useful. You see these used in real life all the time. All right, the next one's kind of interesting. It is used. We don't use it in quite the way that I'm giving my example for it, but that's all right. I wanted to do something that had data from school settings. Scatter plot first before we get there. Scatter plot is often used when a relationship between variables cannot be easily depicted even by a broken line. So it's what a scatter plot does is it plots all the dots everywhere, but it doesn't try to sort of connect them in any way. You're just looking at it and you're going, it's almost like, for those of you who've done geometry, where you kind of squint your eyes and you did your tessellation, you said, what does it look like? It's kind of like that. You've seen those puzzles, maybe you've been to the Science Museum, right? Where you're looking at it and you're squinting and you're like, what does it look like it's overall doing? What do I imagine is happening in the long run? That's what a scatter plot does. It's a far less accurate, like, I can't say, my prediction 3 weeks from now is this. It doesn't work like that. But you could potentially say, well, 3 weeks from now, it looks like it's going to be more than it is today. That kind of stuff. Okay, so that's what a scatter plot does for us in terms of being able to do predictions. The data that I've got here is Coach Lewis kept track of the vertical jump height in inches. This is in inches, if you want to put that in there. Sorry, that's still left out. It's in my notes to put it in there, and I forgot. Of his starters over 8 years. And it's not even 8 years, it's 7 years, which is correct in your stuff, right? It says 7 years. Yeah. Typos on my slides, so sorry. All right, so we have our vertical jump height. So in 2002, he's got these 5 starters. Their jump heights were 65, 63, 60, 62, and 58, all the way down. Okay, so what this looks like is a massive table, or a massive graph with a whole bunch of dots, a bunch of them. Okay, so many so that I need a grid because there's no way I can do this without one. You probably can do it on your lined paper just fine, but it's real hard when you don't have the imagery there. So if you want to just watch what's going on and then fill it in on some graph paper later, I totally get that. If you want to try and create it on your own, you're welcome to do that as well. So we're going to have, just like on the line graphs, we have our time along the bottom. So those are going to be my years. So I have 2020, I'm sorry, not 20, 2002. So I'm just going to label with the last digit, 2000. I'll space them out too. 2003, 2004, 2005, 2006, 2007, and 2008. So these are my, this is the year. I'm going to say year after. Actually, let me shift this just a second. I would like my starting year to be the year 2000. It would make it easier for what I'm about to do in a moment. So I'm about to change something that's going to be a little bit weird for now, but you'll see why I did it later. So just bear with me and recognize that it's helpful to have the year 2000. And even though I don't have data for the year 2001, to have it marked. So these are years after 2000. Okay. Looking in the table that you have here, do you see a smallest value anywhere, a biggest value? What do you see? So there's a 59. There's actually one smaller.
Oh, 58.
There's a 58. Mm-hmm. And what's my biggest?
77.
Okay, I think that's right too. So we're going to have 58 measured somewhere, but we need to make sure that we understand that we're not making 0 the horizontal axis. Like the horizontal axis is not a jump height of 0. So what we do is we actually put a break in the axis to show that, just like this. That way when we start here at 58, we remember that intersect right here is not, like this is not the origin. This is not 0, 0 as an ordered pair. Right? It's not. There's a break in the graph here that's represented differently. So I have 58, and then we're going to go up from there. So 58, I think I'm going to do just one mark for each one of them, and I'll label every other one just like I have before. So this is 60, 62, and I might find that I have too many and I have to change what I'm doing. 64, 66, 68, 70, 72. Okay, so I think I need to get up to 77, right? So I'm going to shift this down and see if I can get there. Um, 74, 76, and then 77 will be on there at 78 at the top. Okay, we're going to make a whole bunch of dots. So I need dots at every one of the heights listed in the 2002 category. So I need one, I need to make sure I'm in the year 2, but also I need 65, 63, 60. $62 and 58. Okay, so that's 1 year's worth of data. There should be 5 dots. And we'll do the next one. 67, 65, 64. 66 and 62. 67, 68, 66. 65 and 64. 68, 70, 67. 69 and 66. 70, 68. 67, 69, and 66. Did I already do that one? Did I just do it twice? Or are they just actually identical? I think I did it twice accidentally. What year am I on? It's supposed to be on the year 6. And I think that's the data for year 6. Double check this one. 68, 70, 67. All right, there's not a 69. That's what's wrong. Okay, I fixed it. Okay, so there's your 5. There's your 6. Your 7, man, we're getting close. 74, 73, and 72. Not in that order, but that's okay. 74, 73, 72, 70, and 69. And then 77, 75. 72, 71, and 70. All right, I need one more thing that I missed over here on the left in terms of my axes, I need to label it, which I forgot to do. So let me shift this over so I have some space to label it. These are jump heights. It's in inches, so somehow I have to write inches in there. This is a scatter plot. So please make yourself a note on this one specifically, because we're going to use the same graph. We're not going to draw it again, but we're going to do a different problem that sort of overlays on top of this graph. But make yourself a note that a scatter plot does not have anything connecting lines together. It's just dots. Okay, so anytime if you were asked on a test or something to draw a scatter plot, you would not connect anything. There'd be no connecting of the dots. All right, the last thing we need on this one is to do a title. These are vertical jump heights. I need to say in inches of Coach Lewis's basketball players. Any questions on scatter plot? Okay, so a scatter plot usually has a bunch of dots that do not connect nicely. Now, in theory, before we actually connected these with lines, it was a scatter plot too. I didn't pause and say that, but it was. I mean, the scatter plot just means the dots that were there before you got the line connecting them. The line itself, when we connected it, is the line graph. There's another type of line that we can create, and it's called a trend line. So a trend line is a line that closely fits the data and can be used to describe it. It's often called a best fit line. So we're doing, because we're looking at mathematics that would be appropriate for middle school and younger age kids, we're talking about a line here. But there's actually nothing special about this being used for a line. People do this all the time with modeling. They try to take data and fit some kind of curve to it. It's usually not a line because that's very specific, but there's some kind of a shape that they're creating to fit to it so that they can try to make a prediction for the future. If you go out and you look at the data, so I did this last spring when we were all stuck at home. They were collecting data every single day for COVID, right? And I was collecting all the data, and all we were seeing when we connected the dots was pretty much a line forever. I mean, for like 2 months, all it was a line. But the perception was it wasn't going to stay a line forever. Nobody expected it to. That was not reasonable. Something was going to change, right? It was either going to go up, it was going to go down. It was not going to stay a line forever. If you go out and you look at the data now, it's a different kind of curve. It's actually called a logistic curve. We talk about it in one of my other classes. And it kind of looks like this, which is exactly what was expected for that data to eventually look like. The question was simply how long would it take before it started doing these curvature kind of features to it. So what we're doing in this section of material is we're looking for a very basic type of a graph, which is a line. Lines are very nice because they're very easy to calculate equations of. Anything else, like this shape, you need far more advanced mathematics to be able to calculate an equation for a shape like that. So we're going to be looking at a trend line for the data. So this is actually our question. It says, using the data in example number 2, okay, the one for the jump heights, create a best fit line for the data. Now, we got a bunch of data that doesn't really have a very defined shape. But at the very least, you can see how it looks like it's sort of swooping uphill, right? You can see that the pattern is that if I were sort of shading it in, it would be shading like this. That's not a very good shade. I didn't get a very thick marker there. Let's try that. The shading is going uphill, right? I'm, hang on. Okay, I kept going. I'm moving in this uphill direction. Does everybody agree with that? So what we're trying to do is we're trying to find a line that has that basic shape to it, and it kind of cuts the data, marginally so in half, so that it's balancing out the data above and below the line. It's not too steep and it's not too shallow. For example, there's some flexibility in what you can draw, but you can't draw this. Not only that, but you can't balance it by drawing it in the middle like that either. That's not the overall shape of what's going on. Are you guys with me? That doesn't look anything like the slope, if you will, of those yellow sort of shaping, highlighting marks that I made before. So there is some flexibility in what we draw, but there is, still an idea of what is and is not acceptable for that shapeability. So the graph might look something, maybe like, that wasn't what I meant. I don't know why I let go of there. Maybe something like that would be reasonable. Does that look like the overall shape of the graph? It does. It's pretty close. We're eyeballing it here. Let's be real. We're eyeballing it here. But what we're doing is we're trying to find some sort of an approximation to allow us to make claims about the future. What does the data look like the next year or the next 2 years or the next 3 years? So we're going to sketch what we believe is an approximation for the line that would sort of cut the data in half, give an overall feel to what's going on the graph. And this is the trend line. I'm going to write it even down that I did this in purple. So if you're looking back at this later, you'll understand. The trend line is the purple thing that we did. The scatter plot was all the dots that we originally had. Part B is where we actually jump back into doing some calculations part of this. Part B is wanting us to find an equation for our trend line. Now, your line and my line might not match up perfectly, and that's fine. Have no problem with that. If I'm grading it or the grader's grading it, they're looking that your equation matches up with your line. All right? So what are the features that you need for a line? Well, one feature you need is you need to be able to calculate slope. Make sense? Another feature that you need is you need to be able to calculate the Y-intercept. So we're looking for, or we're needing to find the slope and the Y-intercept. That's what we're looking for on that purple line. I'll do this whole problem in purple to remind us that we're in purple. The reason is because we have y equal mx plus b as one of the ways that we can write an equation of a line. It's not the only one, but it works pretty well for the purposes of what we're doing here. So, a little bit ago, I told you I wanted my y-axis to start at the year 2000. I wanted that so that we would all be starting at the same place, so that we would all have approximately equal y-intercepts. Okay? So we all started roughly at the year 2000, hopefully. And what I'm looking for is on my graph or on your graph, where did your y-axis actually get hit by the purple line? Mine got hit at 58. When I drew it originally, it was hit at 59 before I shifted it a little bit accidentally. So somewhere in that ballpark is what we're looking for. If your y-intercept is at 52, you've probably made an error somewhere, or you've started at a different location. Not necessarily wrong, but you have to describe it differently. So this is my y-intercept on my graph. It's 58. So that's the number at the end. Now the m in the middle there, the slope, you can either look at it from the perspective of counting on your graph, because it's not too bad, right? On the graph here to be able to sort of count rise over run. But at the very least, what you really want is you want to be able to find actual corners. That's why a graph is like grid paper is really helpful for this, actual corners that it crosses at. For example, on this graph that I'm drawing, this is pretty close to a corner. That's a height, this is the year 2, right, for the 2002, and it's a height of 62. And I'd like to find another one where it looks like it's crossing just about like that too. This one actually here is really nice. So that one is the year 2006, and I'm at a height of 69. It doesn't matter which 2 points you take, you just need to make sure you're taking points on your line, not just random points of the scatter plot. Okay? So those are the two that I'm going to calculate. I'm going to calculate it right here so I'm not flipping back and forth between screens. I believe that this one is approximately 6 and 60, what did I say, 67? 69. And this one over here was 2 and 62. So if you remember, slope is the change in y over the change in x, or it's rise over run, or it's y2 minus y1 over x2 minus x1. You can use any of those that you like, doesn't matter. They're all doing the same thing. So whether you're counting in terms of a visual description or whether you're actually doing the calculation with the values, I've written my values down, so will you do it that way. My later Y value is 69. My earlier Y value is 62. My later X value is the year 6. My earlier X value is the year 2. So this looks a lot like it's 7/4. And so you can write that as a fraction. You could write it as a decimal. Yours and mine might not be exactly the same, but they're going to be close. You're going to be somewhere around, this is 1.75 if you do it as a decimal. You're going to be somewhere around 1.5, so probably within like 1.5 to 2, somewhere in that area is probably what you're looking at approximately. So over here on your equation, we now have, I'll do the decimal, 1.75. Okay, this equation has 0 meaning if that's all you do. It means nothing, absolutely unusable, absolutely worthless. What you need in order to make it usable is some language around it telling me what X and Y are. So it's kind of like writing down a key. What is X? What is Y? So we're just going to write it out like this. X is, Y is. This is not how I always do this, but I'm trying it this time because every time I confuse people the way I do it in my other class. What is X? Well, my X-axis here is the years, right? But specifically, whatever value I used, right, the 2 and the 6, it wasn't year 2 and year 6. What was 2? 2002. What was 6? 2006. So I'm actually measuring these as the years after 2000. So I need to write that as part of my key. My X value is the years after 2000. What is my Y value over here? What is my vertical axis? Jump heights in inches, exactly. And so I'm going to write that down as well. Jump heights in inches. Or you can put inches in parentheses like we were on the other ones too. It doesn't matter, but that's how it's being measured. My big old bold note at the bottom, you must have this, or there's no meaning. So taking a look at part C, you'll see why we needed it, at least in terms of somebody else being able to use our equation for anything. Using your equation, what would you predict the jumping heights would be for this year? What is this year? Yeah, so we're in 2021. So what number would I plug into my equation for the year 2021? What would X be? 21. So if I've not identified how to do X, you might accidentally put 2021 inside your equation and end up with something that looks real crazy. So it's still going to be awfully large because it's still predicting really far out from the data set that I have. But, whoops, we would be putting, I didn't mean to there. Sorry, that's from a different approximation. 1.75 times my 21 plus my 58. And we got a fairly unrealistic but correct answer of, it says 94.75 inches from there. Does that make sense? The process, I mean, not the 94 inches jump height. Okay, the last thing here, super easy. Literally, it'll take us the 2 minutes we have left. Association. Association, I didn't actually mention it over here. Association has to do with whether the line has a positive slope or a negative slope. So if the line's going uphill, the slope's positive, so the association's positive. If the line's going downhill, the slope is negative, the association's negative. And if the line is flat, horizontal, there's no association, okay? So on this one, there was a question actually asked here, and I didn't answer it. It said, it was back over here. Did I ask it in the right place? I guess I left it off. It says draw a scatter plot, and then it says to decide if it has a positive or negative association. On this one, I'll write it in purple. Is this a positive or a negative association? Yeah, I have a positive association. But I can do it just as well from equations themselves. So how about part A? Is this a positive or a negative association? It's negative, because I have a negative 2 times x. What about the second one? Positive, because I have a 4, positive 4 times x. And how about the last one? What's the slope on this? It's 0, so it has no association. So keep this in mind then. We will not have a video that I will post for Thursday or Wednesday because we've finished the section of material. You do have the group work and the homework. There are a few places where it's asking you to take a scatter plot and to draw a trend line. You don't have to draw all the dots. If you'll lay your paper on top of that and can see through it well enough, you can just draw the trend line that you're getting without drawing the dots onto your own paper. Sound good? If you have any questions, please let me know. Send me an email.